So basically, the last topic is observing Markov chains. We're going to do it today. We're going to do a little bit more tomorrow, and then that'll be it. And also, your last quiz is due tomorrow as well. Oh, today. Yeah, today is Tuesday. That's right. Yeah. So, so like if you look at, yeah, regarding the quiz, so so like your handbook, right? Chapter 6, it has 3 sections. So one's called like Introduction to Markov Chains, one is regular Markov chains, and there's absorbing Markov chains. It's only on the first, so the quiz is on like, is only on the first one of those sections, but it's also on linear programming as well, so. Transition diagrams, but we'll do some examples of those in a second. So I'll tell you, I'll mention it when it comes up. Yeah. It won't cover that specific matrix, no. But it won't cover what we did today, and it won't cover what we did the last 2 lectures. So it's just like basically, I mean, basically the only Markov chain stuff on the quiz is like, do you understand what a Markov chain is, basically? So transition matrices, things like that. Okay, so yeah, last topic of the course. So actually we kind of did, I mentioned briefly an example of this at the end of last time where we had a Markov chain that had this interesting property that there was some state where if you run the process long enough, then the Markov chain gets stuck in that state forever, okay? That's something related to this, well, we're gonna look at kind of things related to this in this lecture. So let's say an absorbing state is a state that that can never be left, like meaning, so once you've entered it. Okay. So in other words, basically, you have a state where if the process ever reaches that state, it'll just get stuck there forever. So we'll see an example of that in this matrix here. Okay, and then a Markov chain is absorbing if, so there's kind of 2 properties it has to satisfy. There has to be at least one absorbing state. Okay. But that's not good enough. We need something else. So we need it to be true that from every non-absorbing state, it's possible to eventually get to an absorbing state. So from any absorbing state, non-absorbing state, so apologies, this is getting kind of small at the bottom of the board. But what I'm saying here is from any non-absorbing state, you can eventually reach an absorbing state. Okay, this is getting really small here. Okay, so just in words, from any non-absorbing state, you can eventually, if you run the process long enough, you can eventually get to an absorbing state. Okay. Any questions about that definition? Yeah. It should be square. Oh yeah, you're right. 1, 2, 3, 4, 5. I missed a row. Yes, you're right. So what I wanted to do, sorry about that. I wanted this to be like this. Okay, so there's no what, yeah. And then I want a 1, 0, 0, 0, 0, 0 here. Thanks, that would have got quite confusing if you didn't notice that. So sorry about that. This fifth row should not have a 1 here. It should be a 0, but there should be a 1 here. And then the last row, so if you squeeze in this row, so previously I had this one at the, yeah, if you squeeze in a row like this, that should be right. Okay, so my first question, if we look at this example, is basically which rows are absorbing, or sorry, which states are absorbing. So maybe let's do this like thumbs up, thumbs down thing. So first state, is that absorbing? Thumbs up or thumbs down? Is it true that if I enter state 1, then you can never get out of it? So let's try again. Thumbs up or thumbs down? Okay, so probably the concept isn't clear so far. So this one is not absorbing. The reason is, if I'm in state 1, well, I have a 0.2% chance of staying in state 1, but I have a 0.8% chance of going to state 2. Right? So it's possible, if I'm in state 1, I might jump to state 2 next. So that is not absorbing, right? Because absorbing means if I get into state 1, it gets stuck there forever. What about the second state? Is that absorbing? Thumbs up or thumbs down? Yeah. So it seems like everyone who's answering is answering correctly that this one is absorbing. Okay. And the important thing here is that, so this is the second row, and there's a 1 in the second column. What that means is that if I'm in state 1, or sorry, state 2, I have a 0% chance of going to state 1, a 100% chance of going back to state 2, and a 0% chance of going anywhere else. So what this is saying is if I'm in state 2, I have a 100% chance of just coming back to state 2. Right? So that just means you can't get, once you get to state 2, you can't get out of it. You're going to be stuck there kind of on an infinite loop, back to state 2, state 2, state 2 forever. What about this one, absorbing or not? Thumbs up, thumbs down. Okay, I think the concept's becoming a bit more clear. This one's not. This one is because it's the fourth state. And if I look over here, it has a 100% chance of going back to the fourth state. So that one's absorbing. This one's absorbing. What about this one? Thumbs up, thumbs down. Yeah, think about it for a while. It almost looks like it should be thumbs up, and I think I tricked a lot of you with this one. It's got a 1 in it, that's for sure. So basically, if you get into state 6, you've got a 100% chance of going somewhere, but it's not back to state 6. So this is not absorbing because if you get into state 6, it's not the case that you get stuck, you go back to 6 and go back to 6, go back to 6. What will happen if you got to state 6 is it's going to go immediately to state 1. So it's not true that, so if the 1 was over here, it would be absorbing, but the 1 is over here, so it's not. Okay, so having a 1 in that row is not good enough. It has to be in the correct position. I'm glad I included this row because that tricked a lot of you. Is that clear? Yeah. Yeah, because it's not true that if you get into state 1 that you're stuck there. Because if you're in state 1, there's some chance of going to state 2. So absorbing means if you get into that state, like you'll get stuck in that state forever. You'll just keep going back to the same state. So this doesn't have that property because if I get to state 1, it has some chance of just jumping to state 2 in the next step. In this case, so do you mean like that maybe this 1 would make this absorbing or something? No, so if it's in state 1, so this row, you look at the first row and you say it has a probability of 0.2 of going back to state 1 and 0.8 of going to state 2. So it could just leave to go to state 2. If it's in state 6, it's going to go to state 1. But that's not the same as if it's in state 1, it's going to go to state 1. Yeah? That's a good point, yeah. You're right, there's literally no way to get to state 6. If you look at this column, yeah, it's not going to get there. But still, in principle, this is still a Markov chain, even though it's a bit of a strange one, because there's actually no chance. You could have started in state 6, so that's one way to get there. You might have just started there. Any other questions? Okay, so what you're looking for to determine if it's absorbing, you're looking at a certain row, and you want to know, is there a 1 on the diagonal entry? So if you're on row 2, is there a 1 in column 2? Or if you're on row 5, is there a 1 in column 5? But if you're on row 6 and there's a 1 in column 1, that doesn't really mean anything. Okay, so states 2, 4, and 5 are absorbing. States 1, 3, and 6 aren't. However, so now a question could be, is this Markov chain absorbing? Okay, and so what I mean is that a Markov chain with this transition matrix. So we then look at our criteria. It definitely satisfies the first criteria. There's at least one absorbing state. There's like 3 of them, right? So 1 is satisfied because there's lots of absorbing states. Okay. So then what we need to check is it true that from every non-absorbing state, so from states 1, 3, or 6, it's possible eventually to get to an absorbing state. Okay. This is where actually these transition diagrams are useful. So I made a kind of a bright space announcement about these things. But yeah, so for 2, I want to draw a transition diagram. So you're going to need to understand what these transition diagrams represent for the quiz, for those of you who haven't done it yet. So here's the idea for a transition diagram. I write some like kind of blobs. Actually, sorry, I want to make sure I match my notes. So I've got 6 states. I draw a blob for each state, okay? And then I want to draw some arrows to represent different possible like transitions. So for state 1, I know that one thing that can happen is it can go right back to state 1. So this is like an arrow going out of state 1 and back into state 1. And that happens with probability 0.2. Right? So I'm just going to draw an arrow for every possible transition that can happen. So from state 1, I could also go to state 2, right? With probability 0.8. Okay. And basically, if you look at all the arrows coming out of a given state, they should add up to, the probability should add up to 1, right? And that happens here, right? I have a 0.2 for this arrow going out of 1, a 0.8 for that arrow. So this means if I'm in state 1, 20% of the time, I'm just going to go back to state 1, and 80% of the time, I'm going to go to state 2. For state 2, it's an absorbing state. So it just goes back to itself with 100% probability. Okay, state 3, I could go over to state 1 with probability 0.3. I can go to state 4 with probability 0.6. I can go over to state, wait, is this, no, sorry, that was state 3 with probability 0.6. Sorry. That should be like that. It's hard to count all the way up to 6 with all these different states. It goes to 4, okay, thanks. With 0.1. Okay, is that clear? So it's got 0.3, yeah. So all these, hopefully that's somewhat clear. And then state 4 just goes back to itself 100% of the time. State 5 also goes back to itself 100% of the time. And state 6 always goes to state 1, right? Okay. So this diagram is kind of, I mean, it's a little bit complicated, but it's kind of useful for understanding this second property of an absorbing Markov chain. So my 3 absorbing states are this 1, 2, 5, and 4, right? My other states are 6, 1, and 3. And I need to check, is it true that that 6, 1, and 3 can all eventually reach some absorbing state? In this case, it is true, right? Because 1 can go directly to 2 if you follow the arrow. 3 can actually go directly to 4. Or it could go to 1 and then to 2. So it can get to 2 different absorbing states, which is fine. 6 can go to 1, which can go to 2. So everybody can get to an absorbing state. So yes, it is absorbing because every non-absorbing state can reach an absorbing state. Okay. Yeah. The 6, sorry. That one there? Yeah, so what that is, that's represented by this arrow. Because 6, the row is the 6th row, so it's state 6 going to state 1 has a 100% probability, probability 1. So there's no so if you want to find a absorbing state, when you draw the transition diagram, it should be a state that has a 1 on the arrow back to itself, which means once you get there, it's just going to do an infinite loop back to itself forever. Any questions about that? Okay, so note that here we had to show that every non-absorbing state can get to an absorbing state. It doesn't have to be a unique absorbing state, right? Because 3 can get to 2, and 3 can also get to 4. That's totally fine. And also, it doesn't matter that 5, it's impossible to get to 5. But that doesn't matter. I mean, it doesn't have to be the case everyone can get to every absorbing state or anything like that. Yeah. At least one of them. Like, yeah. So like, yeah, so 1 can't get to 4, but that doesn't really matter. It just has to get to some absorbing state. Any other questions? Yeah. That would not be absorbing. Yeah, because, yeah, so actually even if I took this example and I added some more states, like imagine you had a 7th and an 8th state like this. And maybe even it goes like this or something, or, if I added this to the picture, this would be not absorbing because this state 8 cannot get to an absorbing state, right? It can't reach 4, 5, or 2. So this would now be not absorbing if I had something like this over here. Any other questions about that? Okay. Okay, so what we're going to want to do is try to understand the long-term behavior of an absorbing Markov chain. So kind of like what we did with regular Markov chains, but the kind of the properties of these Markov chains are going to be a lot different. So what we learned with regular Markov chains is if I take the limiting matrix, it always just gives you the stationary distribution on every row, which was really nice. But this is not going to be the case for absorbing Markov chains. So kind of an obvious fact here, if you really understand this definition, is that if I start anywhere in an absorbing Markov chain, it always ends up in one of the absorbing states if you run the process for long enough. So kind of a key fact. An absorbing Markov chain always gets stuck in an absorbing state. So no matter where you start. Okay. I don't mean after just one step, but like eventually, if you run this long enough, it's going to go to some absorbing state. So for example, here, if we started in state 1, maybe it'll go back to state 1 and back to state 1 for a while, but eventually, you're going to get unlucky or whatever, or lucky, however you think about it. And it's going to go to state 2, and then it's going to get stuck, right? 3, it could just jump back to 3 for a while. It could jump to 1. It could maybe stay there for a while, but then it's eventually going to go to 2, and then it's going to be stuck, right? So what we want to be able to do is to determine, so our goal will be determine the probability that it gets stuck in each absorbing state. So what I mean is, suppose we started at 3. There's some probability we get stuck at 4. And there's some probability we get stuck at 2. And we want to know what are those two probabilities, basically. Okay, that might not be clear so far, but let's do an example, and maybe it'll get more clear. But are there any questions about that at this point? Okay. So I'm not going to do a 6 by 6 example. That'll be too complicated. Okay, so let's do this 4 by 4 example. So my matrix is, the first row is 0.2, 0.1, 0.3, 0.4. Then I've got 0, 1, 0, 0, and then 0, 0, 1, 0, and then 0.4, 0.1, 0.2, and 0.3. Okay. Let's just call the states 1, 2, 3, 4. So maybe your question could be, you know, I don't know, so starting at state 1, so if you start at state 1, what is the probability of being absorbed into state 2? Okay, when I say absorbed, I mean it's really this thing about getting stuck. So what we're saying is if you start in state 1 and you keep running the Markov chain for a really long time, the question is, what's the probability that when it stops, or sorry, when you reach an absorbing state, you actually reach state 2 and you get stuck there forever? Okay, we can see, by the way, that state 2 is absorbing, right? Because if you're in state 2, you have a 100% chance of going back to state 2. So being absorbed in state 2 means eventually you get to state 2 and you get stuck there forever. Is the question clear? Okay. Okay, so basically I'm just going to go through the procedure for doing this, rather than the theory about why this works, but we might talk a bit more about the theory next time, if there's time. Okay, so there's going to be a few different steps here. So the first step is just going to be to reorganize the matrix a bit. So what I want to do is reorder the states to put the absorbing states first. Okay. And then you want to rewrite the matrix under this new ordering. So which are my absorbing states here? There's more than one of them. Yeah? Yeah, exactly, yeah. You can see 2 is going to go back to 2, 3 goes back to 3. So those are your absorbing states. So let's put those first. And what do I mean by that? That's, if you just try to, I don't know, mess with this matrix directly, there's a lot of ways to go wrong. What I want to do is, basically I'm just going to, I'm going to just change these kind of lists of numbers so that 2 comes first, and then 3, and then 1, and then 4. So I'll just write 2, 3, 1, 4. 2, 3, 1, 4. Okay. Of course, it's valid to do this, right? If I'm just kind of reordering the states, but as long as you don't change anything. So what I want to do is like in this position, right? That's the row for 2 and the column for 2. I need to put the value in that row and column, which is a 1. So, right? And then I put the entry for for 3 and then 1 and then 4. So 0, 0, 0. Okay, and then similarly you have this. Okay. So what I'm representing here is that, like, in my original matrix, in the row corresponding to 3 and the column corresponding to 3, I had a 1, right? So there should be a 1 in the row and column corresponding to the number 3 here as well. This is where things get a little bit more complicated when I go to these two states. So can anyone see what my first entry should be on this row? Yeah, I think so. That looks right, yeah. Right, and I'm guessing you got that from looking at this row and then looking at the column corresponding to the state 2, right? And then we want 0.3, 0.2, and 0.4. Okay, and then we want another 0.1, 0.2, 0.4, 0.3. You got to be really careful in this step. If you mess these numbers up, everything after this is going to be wrong. Any questions about how I came up with any of these numbers? Yeah. Would it make any? Well, this matrix would look a little different, but your final answer won't matter. It won't make a difference. Yeah. So if I put these in any order, it could have even been 3, 2, 4, 1, or as long as you just put your absorbing ones first, your non-absorbing last, it'll be fine. Any other questions? Yeah. Yeah, you want to keep that consistent. So you want to do the same thing that you did here, the same ordering on both of them. Otherwise, it's going to mess everything up. That's going to be important. Yeah. But as long as you do the same thing on both, it's going to be fine. Okay. Now our second step is to divide up this matrix in some specific way. So basically you want to say, okay, so now I know my absorbing states come first, and you want to say, where is the last absorbing state? And I draw a little line. Okay. And then I do the same thing with the last column. So I draw a line between the absorbing states and the non-absorbing states. And I do the same thing with the row. Okay? And what you'll see is up here you've got the identity matrix. Over here you're always going to have the 0 matrix. And then down here and here you're going to have more kind of complicated matrices. So step 2, divide the matrix into something like this, where you have identity here. And these are your absorbing states, and these are the non-absorbing states. These are your absorbing and the non. So this is the identity matrix where the number of rows and columns is equal to the number of absorbing states. Here I've got 0. And here I've got some other matrix, which we'll call R. And here we have another matrix we'll call Q. Okay. So basically the division lines, you just determine them by saying, where's my last absorbing state? And we cut it there and cut it there. And then you've got these two matrices sitting here. Okay, so that's my second step. Okay, so here's a kind of key fact, which I'm not going to be able to justify for you today. But if I take the matrices P and then P squared, then P cubed, dot, 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 where of course this was P. Well, actually, yeah, so I'm kind of thinking of P as being the reorganized matrix, not the original matrix. They converge to a limiting matrix P bar, just like for regular matrices, but it's going to look different than the one with regular matrices. So it's a bit more complicated. So what it looks like, it's got the identity here. It's got 0 here, just like this. But now it's got a 0 here. So this was a Q before, not a 0. Note this little line. And over here, it's got something quite strange. It's got the matrix, the identity minus Q inverse times R. Okay. We'll do this in this example, but yeah, what you want here is take the identity matrix, which is just the matrix with ones on the diagonal. And you want the identity matrix where so the size of this, so the number of so like here, I'm not really telling you how big these matrices are, but for this one, it should be the number of rows and columns is equal to the number of non-absorbing states. Okay, and for this one, it should be that the number of, of absorbing states is like the number of rows and columns. So in this case, it's not going to matter because we've got 2 of each, but generally it could matter. Okay. So what we're going to do now is find the this limiting matrix. Yeah. Oh, what I mean is like the size of this I, the number of rows and columns is equal to the number of absorbing states. And like the matrix in here is you take that thing minus Q, take the inverse, multiply it by R, and then you write that matrix in that box. But yeah, all I'm saying is that's how, in case you're wondering like, oh, what size of identity matrix should I take? It should be the size where the number of rows and columns equals the number of non-absorbing states. So in this case, it should be 2 by 2 because I've got 2 non-absorbing states. Yeah, so this is quite weird, but let's go with it and see what happens. So our third step will be to compute I minus Q inverse. Is this third step or fourth? Yeah, third. Okay. So we have to go back and say what was Q again? Q was this matrix in this bottom right corner. So 0.2, 0.4, 0.1, 0.2. So I minus Q will be 0.8, negative 0.4, negative 0.1, and, oh, sorry, this should have been a 0.3, I think. Right? That's a 0.3 right there. So this is Q. So that should be a 0.7. Okay. How would I get the inverse of this thing? Yeah. Well, yeah, you kind of set it up in a Gauss-Jordan thing with the identity, and then you row reduce, or Gauss-Jordan elimination. So yeah, to find the identity, I stick this in a matrix like this. The line, and then 1, 0, 0, 1. Okay. So this just goes back to the, yeah. Probably, yep. Thanks. Yeah, thank you for that. The term's almost over, and now I'm like doing all the typos here. Okay, I guess I'm getting careless. But yeah, so you guys have done a lot of Gauss-Jordan by now. So let's, so maybe I'll skip this because we are a little bit short on time, maybe. So I'll just say we do Gauss-Jordan. I mean, this is only a 2 by 2. Probably you guys could work that out. And then what you end up with is, so the matrix will now look like 1, 0, 0, 1, 7 over 4, 1, 1, 2. Okay, so therefore, I minus Q inverse is the matrix you get over here. Okay. So all we're doing is like we do the Gauss-Jordan elimination. But I'm just kind of skipping that. Okay, so that was my third step. My fourth step will be to compute I minus Q inverse times R. Okay, so we already know what so this is just a matrix multiplication. We already know the inverse. It's 7 over 4, 1, 1, 2. We know what R is. It's whatever is here. And probably I'm going to write it down wrong. That seems like the theme today. Everything I write is slightly wrong. Okay, I think I got it this time. Just a bit of matrix multiplication, and then you get, if you do it correctly, which I'm not guaranteeing I've done, you get 0.275 here, and then 0.725 here, 0.3 here, and 0.7 here. Okay. So now, if I use this kind of fact here, what it tells me is my limiting matrix We should remember our states are ordered 2, 3, 1, 4. If you remember, that's how we reordered them. So 2, 3, 1, 4. My limiting matrix will look like 1, 0, 0, 1, 0, 0, 0, 0, 0.275, 0.725, 0.3, 0.7, and then 0, 0, 0, 0. Okay. So this is my, this is this matrix, right? We just computed it. And now this limiting matrix tells us all the information we need. So this tells us what happens when we run this matrix to infinity. So if you start in state 1, remember state 1 is now the third row, right? What this is saying is that you have a 27.5% chance if you do this infinitely many times, you have a 27.5% chance of eventually getting stuck in state 2. So you have a 27.5% chance of getting stuck in state 2 eventually in the long term. Okay. And obviously, if you started in state 2, you have a 100% chance of ending in state 2 because state 2 is absorbing, so it just goes back to itself over and over. State 4, if you started in state 4, you have a 30% chance of ending up in state 2. Okay? And if you think about it, it makes sense if I add up this row, actually one thing that could go wrong, if this doesn't add up to 1, you've got a problem, right? You should have some, if you have some chance of ending here, 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 or here, it should add up to 1. Yeah? State 3, yeah. So we want to, it's important to remember this kind of order here. So state 4, 70% chance of ending up in state 3. Yeah. And it makes sense that all of these are 0 because you can never end up getting stuck in state 1 because state 1's not absorbing, right?